Hello, my name is Sarav, and in today's video, we will be taking a look into interference and diffraction. Before we take a look at light, we must first understand how waves work. In AP Physics 1, we learned that when two waves meet, they experience interference, either constructive or destructive. Constructive interference occurs when the crest of one wave meets the crest of another wave, and the trough of the first wave meets the same trough of the second wave. While destructive interference works when the crest of one wave meets the trough of the other wave, canceling them out. To see how this concept correlates to light, we can take a look at Young's double-slit interference experiment. The experiment is set up so that on the left we have an incident of light, followed by a metal sheet with two narrow slits in it. On the right we have a screen. The distance L between the metal sheet and the screen must be much larger than the distance D for this experiment to work. Now we must ask, how will the light travel? We might expect to see two bright narrow strips of light directly opposite the slits in the barrier. As reasonable as this may sound, it doesn't take into account the wave nature of light. In fact, when light travels through a small opening, as in this experiment, it spreads out. This alteration in the straight line propagation of a wave is also called diffraction. As seen in the image, the waves diffract through the slits, causing them to interfere with one another as they move towards the screen. Just like the waves we talked about at the start of the video, light waves too have troughs and crests. As a result, we get constructive and destructive interference during this interaction. Looking at the screen view of the image, we see that where the waves constructively interfere, there are bright bands, also called fringes, and located where the waves deconstructively interfere are dark fringes. When we conduct the experiment, we get something like this. Here you can clearly see the light fringes as opposed to the dark fringes. Using this experiment and some geometry, we get the following equations. The constructive interference equation gives us the mode at which the wave creates maximum intensity bright fringes. This equation relies on d, the distance between the two slits, theta, the angle between the point on the screen and a slit, and lambda, the wavelength of the light wave. The destructive interference equation is similar, except that 1/2 is added to m, because this is when the crest of one wave will meet the trough of another. The final equation is used to give us the exact position of the light fringe or the dark fringe on the screen. So finally, here are some extra important notes about this experiment. The intensity of the bright fringes decreases as m increases in magnitude. So essentially, as we get further up or further down the screen, the intensity of the light decreases. The bright fringe directly opposite the midpoint of the slits, the central maximum, will have the greatest intensity. If more than two slits are cut in the barrier, the interference becomes sharper and the distinction between light and dark fringes becomes more pronounced. In fact, diffraction gratings are used precisely for this purpose. They contain thousands of tiny slits per centimeter, and as a result, when the light flows through, it creates varying light colors, which is quite magnificent. But that's a video for another day. Thanks for watching my video. I hope you enjoyed and learned something new.